Hello, my name is Michael Schertz. I'm coming to you from beautiful Boulder, Colorado, and I'll be talking about modeling chemically specific separations in lyotropic liquid crystal self-assembled nanoporous membranes. Acknowledgements. The vast majority of this work was done by Ben Kasha, who is who's a graduate student that recently graduated from my group and is now working for Schrodinger Materials Science, funding from ACSPRF, and a number of collaborators who helped us both with experimental and theoretical aspects of this project. All right, so standard membrane-based separation techniques are energy intensive with frequently limited selectivity. Reverse osmosis membranes, typically a thin film composite with a pore supports and a very dense polymer matrix active layer. Now, these are generally highly selective because of the very small sizes you can get, but generally have low permeability and thus high energy needed. Nanofiltration membranes generally have pores on the order of 1 nanometer, and they separate based on the size of the molecules, but are tortuous and polydisperse in pore size, which frequently hurts the selectivity. So we really want to have new solutions for selective separation membranes. There's been a lot of interest over the last 10 years in nanostructured membranes, which have unique material advantages because of the very precise sizes that one has. It's carbon nanotubes and graphene oxides. These are all different molecules with interesting properties that people played around with. But for all of these, there's a lot of formulations issues, aligning carbon nanotubes, getting the right pores in the right places with the right functionalities for graphene or graphene oxide. So I'm going to be talking about a different platform for separations technology. So lyotropic liquid crystals can be designed for solute-specific separations because they self-assemble into nanochannels. And importantly, you get a lot of functionality. The choice of functional head groups and counterions that can affect the channels that are formed, the length and number of tails as well affect these. And so by changing these parts of the monomer, you can potentially control pore size and also the chemical environment of the solutes going through and controllable crystalline phase behavior. For example, these monomers generally form hexagonal phases, while these other monomers form bicontinuous cubic phases. So you get these hydrophilic channels through which water-soluble molecules can flow. And this is being used for separations right now at the laboratory scale. We're interested in using molecular dynamics to connect nanoscopic pore structure and macroscopic performance. Can we use modeling to understand what's going on and then propagate that information up to a macroscopic scale? Before doing modeling, you had guesstimated pictures and a few experiments to provide understanding of what's going on. You know essentially the overall morphology, but it becomes hard to understand exactly what's going on. The picture that you get is, well, if these hexagonal phases, you've got 5, 6 maybe, who knows, monomers arranged around these pores. You know the pore distance, the distance between pores from some X-ray scattering, but that's about it. But with modeling, we can get a much more complete picture of exactly what's going on with the molecules. To try to understand what's the mechanism for transmutive solutes, how can we modify lyotropic liquid crystals monomers to control membrane selectivity, and how can a model be used to directly design future membranes. So I'm going to skip a lot of the details of the configuration build procedure. You can look at some of Ben's papers to understand that better. But this is what the membrane cross section of the membranes look like, where you have these water-filled pores surrounded by the hydrophobic tails. This hexagonal phase is stable within a range of water contents. Different experimentalists have come up with different numbers. We're generally going to be studying the phases with about 10% weight water. Generally, if you have too little water, then transport of everything gets very slow. We're obviously going to be interested in situations where you have a moderate amount of throughput. So we're looking at ones that have a moderate amount of water in the pores because those are the ones that have fast enough transport to be useful. So an important thing is these are not really homogeneous pores. If you look at the structure of this molecule, if you look at the radial distribution, the distance from the pore center, you can see that it's not like a pipe. The water has high concentration at the center and then gradually decreases as you go along radially out from the pore. The sodium, the counter ion for the head group, is spaced out moderately all the way from 0 to 0.8 nanometers. The tails actually have moderate contribution, out in as far as 0.8 nanometers. And so it's hard to say what the effective pore size is at this point, because it will depend upon what sorts of groups you're interacting with in the molecule. So we go through the build and we run the simulations, and this is where it really gets interesting. So this is the output of our modeling. In this case, the gray are the tails, the blue are the head groups, the white and red are the water, and then the orange and the solute. So what we need to do is take simulations like this and turn this into mechanisms, turn this into transport equations that we can use to describe macroscopic behavior. So what we do see when we start analyzing this is that solutes show subdiffusive behavior with intermittent hops between long periods of entrapment. So here's 3 represented ethanol center of mass trajectories, and you can see yellow means closer to the center of the pore, and they're jiggling around quite a lot. They move more frequently there. And the purple is out further into the hydrophobic region, and you can see that it can get out there, but it gets stuck when it's out there. Analysis shows that solutes experience at least 3 different trapping mechanisms. They could be entrapped among the monomer tails, and some chemicals experience that more than others. You could have hydrogen bonding with the monomer head groups. Obviously, only solutes that can hydrogen bond actually do that. And it turns out that association with the sodium counterions can actually be quite important as well. Different ways they can get trapped. So each different molecule is getting trapped in different ways for different amounts of time. And so one thing that we've really been focusing on recently, and we recently published, is to try to use state-based models, learn from the dynamics in order to facilitate understanding the mechanistic hypotheses, rather than just staring at the structures and trying to figure out what's happening where, is to use the details of the dynamics and how it jiggles around, and actually learn and partition the different dynamical segments in ways and group them together, and then use those to tell us where we should be looking for interesting structural quantities. So here you can see you can actually go back afterwards and say, oh yeah, well, it's trapped in the tails here, it's rattling around the central pore here, and it's hydrogen bonding here. But what if you could use the dynamical properties, how much it wiggles, how far it jumps, what the autocorrelations are in its motions, in order to figure out where you should go look for structural behavior to understand the mechanisms better, because these get very complex. You don't just want to stare at structures to figure out what's going on. So Ben really pioneered a way of fitting these to autoregressive models, where you can detect and parameterize an unknown number of hidden dynamical modes, where you parameterize each state as a vector autoregressive process of order R, and then use Bayesian inference in order to determine how many different models there are and what those parameters are. And so, and then after doing this process, you cluster the parameters in order to reduce the state space. Sometimes there can be hundreds of different states that can be clustered together. And then we can look at the parameters of these and build chemical intuition with detailed visualizations of solute behavior. Once you know the states, that where, at each state is where the molecule is behaving in a certain way, then you can look at things like the local density around the solute, the hydrogen bonds that are being formed, and the sodium association, and correlate those behaviors with the dynamical state and learn the mechanisms that way. So once we do this, we've been working in connecting microscopic and macroscopic transport scales. Even though these are subdiffusive and it's very hard to actually get to run them long enough and for large enough spaces to get diffusion coefficients, once you have a dynamical model, you can actually run that dynamical model out to very long time scales. So, for example, the absence of convective flux, you can look at the cell activity of solute I over solute J is related to, we can make the flux from, use related to the flux, and we can relate that flux to mean first passage times. So these mean first passage times, we can simulate, even though we can't simulate them with molecular dynamics, we can simulate them with the stochastic models that are fit from the molecular dynamics. Get mean passage time distributions, and from that, calculate macroscopic diffusion constants over very large length scales for a membrane and time scales. And so what we could do is then build, working on doing it, and Ben has put most of this work together, is to build a general selective transmate workflow to help us design, where you simulate a monomer, you build systems and simulate the sites of interest, and apply this infinite hidden Markov model to identify how many states there are, what their properties are, use that to identify transport mechanisms, and then from that predict macroscopic observables. For example, although these particular experiments had not been done, we can look at different selectivities of different solute species based on the mechanisms we observe. And the goal, and this definitely hasn't been done yet, is to take these observables, understand what is occurring in the transport, and then propose new monomers. So the take-home messages from this is the heterogeneous poor environments of self-assembled nanochannels suggest that the possibility for chemically selective transport. And we can fit this complex subdiffusive transport that you need to run out you can't really get good diffusion constants even if you're running out for microseconds. We can fit this transport to stochastic models that can be run out to long time scale. And we can use these stochastic models to both identify potential mechanisms and propagate out to longer scale without an explicit formula, and find new ways to connect, not just simple transport, but very complex molecular level transport to macroscopic behavior that we can hopefully use to help our experimental colleagues to design better membranes. Thanks so much for listening, and I'd be happy to take any questions in the various internet channels that exist. Thank you.